Welcome back, children. When we started this lesson, we said that current will produce magnetism. In fact, we said there is no magnetism without current. Current is nothing but moving charges. But what happened later is that instead of talking about the magnetic field produced by this current, the moving charges, we were focusing on moving charges in an external magnetic field. So this is what we have done so far. But now we will focus on the magnetic field that the moving charges produce. Okay? So we'll take a long wire. Okay? Let's suppose that the wire is going into the board. So if you see the wire from here, all that you see is just a dot. So current I is flowing into the board. It's a long wire. So we know that magnetic field lines will be set up by this current around the wire. So the direction of the field will be given by the right hand rule. So if you take the thumb as the direction of the current flow, then the way the finger, the other four fingers curl, gives you the direction of the magnetic field. So it's going to be like this. As I said, the current is going into the board. Countless experiments have proved that the magnetic field, let me take a random point here, this point, let's say. Magnetic field at this position, B, okay, this was proportional to the current flowing through the wire. Meaning that if I increase the current flowing through that wire, then B at this point, at any and every point, will also increase. And it was also established that B was inversely proportional to the distance. So the farther you go from I, the smaller the field strength became. But this is the factor by which it was falling off. As R increases, B was falling, and it was falling with this factor. Okay. So if I combine this, then I'll say B is proportional to I by R. And I can introduce a constant of proportionality, and then B is equal to, say, some constant C and I by R. Let me call this as CB. Okay. The constant for the magnetic field or something. So this is what you get. So it was found out that this constant CB is a very small quantity. So B, actually let me put C, that CB is considered to be 10 to the power minus 7. So it's very, very small. So this is going to be equal to B is equal to 10 to the power minus 7 into I by R. So B is going to be in Tesla, then I is going to be in amperes, and then R is going to be in meters. So this is what has been experimentally proved for a very long current carrying wire. The two scientists, Biot and Savart, don't read their names as Biot-Savart. Okay, this is Bio, it rhymes with Leo, and this Savart rhymes with bazaar. So this is how you pronounce their names. So Biot-Savart. So they looked at this and then they found a similarity between this and the electric field, not the magnetic field, the electric field produced by an infinitely long charge. So you also have come across that in your electricity part of your plus 2 portions. So if you take an infinitely long thin wire which has charge on it, with charge density lambda, then it's going to produce field around it. Again, I am seeing it from this perspective. That line, that infinitely long line, also goes into the board. So field lines will be produced like this. Okay. And this field strength was given by this equation, E equal to lambda by 2 pi epsilon naught r. So lambda is the charge density and r is the distance from that line, infinitely long line, and this is a constant. So I can write it like this: E is equal to 1 by 2 pi epsilon naught to lambda by r. So this is a constant, so let me call it as constant of, say, electricity or something, and lambda by r. So I look at this now. Look at this equation, look at this equation now. They are similar. For a long current carrying wire, the field around it is given by this equation. For an infinitely long line of charge, the electric field around it is given by this equation. So the direction is different. Let's not worry about the direction. We're just talking only about the magnitude. Let's not worry about the direction now. The magnitude is given by this. The magnitude was falling off as r has increased. Okay, like lambda by r. Again, I by r. So there is a similarity you can see between these two quantities. Now, these two scientists asked this question. Okay, why does this happen? This happens because of Coulomb force. What is the Coulomb force? Say it's like if you have an electric charge Q, it's a point charge, then E for that point charge Q, E is given by 1 by 4 pi epsilon naught to Q by r square. Because this was true for a small charge, this is true for an infinitely long wire. So, for this long wire which carries current, this is true, which means that if there is a small charge, like it's a point charge, magnetic charge or something, okay, then that should also follow this kind of a structure. So the field produced by a magnetic charge, okay, can be treated to be similar to this. So let's compare the quantities. So you got E is equal to C lambda by R, and then you got B is equal to some constant CB into I by R. So this is a constant, this is a constant, this is R, this is R. So lambda is similar to I. But how is lambda related to Q? lambda is related to q. Now, how do you get q from lambda? It's like if you take a long wire, then let's say, let me draw this here, okay? So, if you have a long wire, lambda as the linear charge density, and if I take a small length dl, then the charge in that must be equal to lambda dl. So that's your dq. So likewise, if there is a magnetic charge, let us suppose, okay, then that would be given by I is the current flowing through this wire, and if I take a small length of that I, of that conductor wire, so this is dl, then I dl must be equal to what I would call as a magnetic charge. This is electric charge, dq, clearly. A small charge, it's dq. I'll call this as electric charge and I'll call this as magnetic charge. I put that in code. Okay. Why? This is true because you have electric monopoles. You have positive and negative charges separately in the case of electricity. But in magnetism, so far we have not come across a monopole. A monopole is single pole. So what does it mean? You will get only a north pole or only south pole, like you have proton and electron. So far we have not come across that. We have not found, nobody has found a magnetic monopole. So that is why I am just putting that in code. But if it were to exist, then that should have this dimension, I to dl. Because electric monopole produces this kind of a field when arranged in an infinite long line. Likewise, this magnetic monopole should produce this B if it is on an infinitely long wire. So I into Tn will give me this. So if this is it, then what should my B be? D cubes lambda dl, then I can get a dE. Likewise, what should be the field value if this is the value of the magnetic monopole, is what we will see now. Okay. So Biot-Savart, by comparing the infinite long line of charge and the long wire carrying current, concluded that if there was a magnetic charge, then that must be similar to the electric charge. And they also came up with the quantity that would resemble this magnetic charge. Okay, that is lambda L, said. Sorry, IL. So now let's take it further. I have an infinitely long wire which carries electric charge Q. Okay, linear density lambda. Okay, this kind of carries electric charge with linear charge density lambda. Suppose I take a very small length dl. And what's the charge in it? This is going to be dq is equal to lambda into dl. So that's a charge contained in that small length. And if I want to find the electric field set up by this charge at some distance r, let's say this is where I want to find it. So I have some distance r. So this is the point P at which I want to find the electric field set by this small charge dq. Then what would I write? So dq, it's a small electric field, right? So the field will be in the same direction as the radius vector. So like that. So this will be dE, small charge, small field. So dE is equal to 1 by 4 pi epsilon naught into dq, that's a charge, by r squared in the direction of r. Okay. So this would be 1 by 4 pi epsilon naught to lambda dl by r squared in the direction of this. So there are many dls here, very small lengths. So all these charges will put their own field at this point, and then the resultant field, electric field, will be the vectorial sum of all these individual electric fields put by these small charges. So let's not get into that, but I know that this dE is going to be something like this. This we already come across. Now let me extend the same idea to the magnetic field. So I have a wire, so current I flows through it. Then let me take a small distance dl, and now I am going to calculate the magnetic field at some point, say r, from here. Okay, this is r. Current is moving in this direction. I want to find the field at this point. So how do I do that? Okay, same. I'm going to get dB. That is equal to, we saw it before, that there is this constant Cp, okay, and there must be I dl, right? So I is here, magnetic charge. I call this as a dq yam or something, by r squared, by analogy. But what is my dqm? My dqm is Cb into I dl by r squared. Just like this. So look at this. What is this 1 by 4 pi epsilon naught? This is what we called as Ce. Ce is equal to 1 by 4 pi epsilon naught. When we made this comparison, we used the symbol Ce for this quantity. So in line with this, in line with the same thing, I am going to write Cb as mu naught by 4 pi, just in line with this. So this is equal to 10 power minus 7 anyway. So this is equal to 10 power minus 7, that's what we said. So mu naught will be equal to 4 pi into 10 power minus 7, but let me not get into that. So this is my Cb. So what do you get here? So dB is equal to mu naught by 4 pi mu naught by 4 pi into I dl by r squared. This mu naught by 4 pi is simply 10 power minus 7, but just to be consistent with the previous one, I am doing this. Okay. This mu naught is called as a permeability of free space. Epsilon naught is permittivity of free space, and mu naught is permeability of free space. Okay? So this will be the magnitude of the magnetic field B at this point. But what about the direction? Well, I told you that we should be using the right hand thumb rule. Okay. So if the current is going like that, then if I curl my fingers around this, then notice that at point P, and B is going into the page. It's not coming out as well as coming out like DE. The DB would be going into the page. Then how do I account for it? Then I can have a vector algebra approach to this to find direction. Well, I have I in this direction, but current is not a vector quantity. But what can be a vector here? dl can be a vector. So I can take dl in the direction of the current and then call that as the vector quantity. And I have r, the position vector of P from this dl. That's a vector quantity that I can consider. But I need to get this direction which goes into it. Then it's going to be perpendicular to this, right? So then what should I do? Then I can go for a vector cross product. So IDL, I is in this direction, R is here. So IDL is in this direction, R is here. So IDL cross R, and then you notice that you get the direction into it. So then I'll say the next step, if I need to get direction, then I'll say dB is equal to mu naught by 4 pi into I dl, is the I into dl, it's a vector, cross, what I'm going to do? I'm going to ideally R square L just put, but what do I need here? I just need the direction. I don't need any magnitude, right? So then I'll take the unit vector along this direction, which is r cap. Not r, but the unit vector along this direction. Then the magnitude does not change, because the magnitude of r is 1. So I'll take that and so this is going to be r cap. Or I can expand r cap as the entire r by the magnitude of r. So in that case, mu naught by 4 pi I dl cross r, the entire r. Notice it, I've got a cap here, I've taken the entire r. So this is divided by r squared into this r by r will give me the unit vector here. So r squared by r squared into r. So I get this equation. So now dB is equal to mu naught by 4 pi I dl cross either unit vector, in that case it's going to be r squared, or mu naught by 4 pi I dl cross the whole vector, in that case it's going to be r cube. So this is called the Biot-Savart law. So this is called Biot-Savart law. So, Biot-Savart law allows you to find the magnetic field at any point due to a current element. So, this ideal is called as a current element. So, Biot-Savart law helps you do this. Hope you understand this law. As an aside, I want to talk about the two quantities, epsilon naught in electricity and mu naught in magnetism. So, this epsilon naught is called the permittivity of free space, and mu naught is called the permeability of free space. Let me take these two quantities and then multiply them and then see what you get. So, mu naught into epsilon naught into mu naught. So, this can be written like this. I'll take this and then multiply this by 4 pi and divide it by 4 pi. 4 pi by 4 pi to epsilon naught mu naught. Okay. So this will give me, I'm going to rearrange them. I'm going to take this together. Okay. 4 pi epsilon naught into mu naught by 4 pi. So, but what was this 4 pi epsilon naught? We know this, right? We know that 1 by 4 pi epsilon naught was equal to 9 into 10 to the power 9. That was the value of this. And what was this value? Mu naught by 4 pi is equal to simply 10 to the power minus 7. This was simply CB and this was our CE. So, if I plug in those numbers, it's 1 by 4 pi epsilon naught is equal to 9 into 10 power 9. So, 4 pi epsilon naught will be equal to 1 by 9 into 10 to the power 9. So, multiplied by 10 power minus 7. So, what am I going to get now? I'm going to get mu naught to epsilon naught is equal to I'll bring it here 1 by 9 into 10 to the power 9 into 10 to the power 7, that's equal to 1 by 9 into 10 to the power 16 mu naught epsilon naught. But notice here 9 into 10 to the power 16 is 3 into 10 power 8 the whole square equal to 1 by 3 into 10 power 8 the whole square. But what is 3 into 10 power 8? That number is actually the speed of light. So I get 1 by c square. So epsilon naught and mu naught gives you relationship. Or from this I can say C is equal to 1 by square root of epsilon naught. So electricity and magnetism. Gives you some kind of an idea, a vague idea, that light could be a combination of electric and magnetic fields. Because this is the speed of light. We'll talk about it later in much more detail than this, but just by looking at these quantities and multiplying them, then you get this expression. You get the velocity of light in some way.